Yeah. Thanks all for coming in, and thanks Rajesh for inviting me for this. And we'll continue from where we left off yesterday on our discussion on the Lovasz theta function, the semi-definite programs and algorithms on it. So yesterday we had mostly talked about the Lovasz theta function, right? Um, and we had seen some motivation for how it came about, why did we define those quantities and this connect to geometric representations of graphs. So let me quickly recap that. And in the first part today, I will be proving a structural result using something called that goes through something that has since been come to known as semi-definite programming. Okay. And in the next part, we will mostly deal with algorithms arising out of it. Okay. So this was what we more or less covered yesterday. Okay. And this is going to be the plan for today. I'm going to start with some introduction to linear and semi-definite programs and then prove something. The main result that I will discuss in this first part is something called the sandwich theorem. Okay. Proven by Lovasz. And for that, the way we'll approach it is actually take a detour through computation. Although the theorem itself is going to be a structural result about graphs, I'm going to take a detour through computation, introduce these semi-definite programs, and then use that to show the theorem. And in the next part, in the second part, I'm going to talk more about how semi-definite programs are actually useful for approximating various quantities, okay, related to graphs in a computational sense. So as before, please feel free to stop me at any point to ask questions or get clarifications. Happy to stop and answer. Good. So let's go over a quick recap for what we did yesterday. We first said that alpha of G, the independent maximum size of the maximum independent set in a graph G and its chromatic numbers are hard to compute quantities computationally, but are important from both theoretical and practical standpoints. In particular, we were interested in this quantity, S of G, which was related to something called the Shannon capacity, which I defined yesterday. But I can look at it just purely from a graph theoretic sense that it's the supremum over all possible k in natural numbers of the maximum independence number of the maximum independent set size in the product graph g to the k. Okay, I'm not going to define what product graph is. We did it yesterday. I'll not repeat it again. Raised to the power 1 over k. Okay. And this had some relation to the amount of information a channel can send across without confusing certain characters. And what we had seen in the second part yesterday in our second lecture is that Lovasz came up with this formulation of a function of the graph, which we call the theta function. Okay. Um, that satisfied that it was always an upper bound on this quantity S of G that we are interested in. Okay. And why did Lovasz introduce this? Lovasz introduced this because it satisfies certain nice properties that allow us to analyze the graph product. Okay. In particular, it satisfied that the theta function has this multiplicativity property that theta of G of the k-fold graph product is at most the theta of the original base graph raised to the power k. Okay, in fact, it is equality, but we didn't prove the equality. We proved the inequality yesterday, right? And then using this, Lovasz could show that for this very nice graph C5, um, the Shannon capacity is square root 5. Okay, and the representation, and if you recall again, and we'll do it in the next slide, the theta function is related to a certain geometrical representation of the graph G, which we called orthonormal representation. Okay. Okay, so Lovasz's result basically showed that the Shannon capacity or S of G of C5 is square root 5. Okay, and computing this S of G for even simple graphs G is very hard and we don't, or hard to analyze and we don't know how to do, okay, to find what the value is analytically. Good. So here's where we're going to begin from. Let's recap what an orthonormal representation is for a graph G. And most of the rest of the lecture will be regarding the theta function and will not deal with S of G directly today. Yeah. Good. So an orthonormal representation for a graph G is a set of unit vectors. u1 to un. I should be careful over here possibly and say that the vertex set of the graph is going to be identified with the set 1 to n. So the vertices are labeled 1 to n, and the vectors u1 to un are um, basically an assignment of one vector per vertex. Okay. And the condition that we wanted to satisfy, this representation to satisfy, is that ui transpose uj is 0. That is, two vectors are orthogonal. Maybe I should not have. That if ij is in E bar, got this wrong, then ui transpose uj should be 0. Okay. So this is a mistake here. It should not be if and only if. It should just be an if. Okay. If ij is in E bar, then ui transpose uj should be equal to 0. That is for every non-edge in the graph G, the correspondingly assigned vectors are orthonormal. Okay. Now, there are certain orthonormal representations that are very nice. Right. In particular, the niceness of an orthonormal representation is going to be based on a certain value that we assign. Okay, and the value of an orthonormal representation is the minimum over all vectors C with norm C equal to 1 of the maximum over I of 1 over C transpose UI square. Think of C transpose UI as a projection of the vector UI on the vector C, on the unit vector C. You're taking the inverse of that, taking the square. We had seen good reason for why this is useful for us yesterday. And finally, the theta function of the graph G is the minimum over all possible orthonormal representations for the graph G of the value of the orthonormal representation. Okay. So I'll leave this for a moment while you look at it. If you have any questions, please stop me and ask me in case you want me to go over some of this again. So the vector C over here is called the handle. Okay. Okay. Any questions? Good. Okay, so let me go ahead from here. We're going to use this definition again and again. If you recall, there was a non-trivial orthonormal representation that we had seen for C5, which was basically visualized by folding this umbrella, right? So you start off with all the spokes completely open, and then you kind of open it out, right? Until the actual vectors that you need to be orthogonal are actually orthogonal. Okay. For instance, you would want U1 to be orthogonal to U3 and U4, and you'll see that you can always fold the umbrella out to a certain angle such that this happens. Okay. And we had kind of given the coordinates for this and verified that it has a value of square root 5. Okay. So I just need one more definition for today. I'll use this. It's not very, it's quite trivial. Basically, I'll call small omega of G to be the size of the maximum clique in G. Okay. And recall that this is really related to the size of the independent set, because what can I say about this? If I look at the independent set in the complement graph, right, this is equal to size of the clique. So every independent set in the complement graph corresponds to a clique in the original graph, right, and vice versa. So therefore, I can always say that alpha of G bar is equal to omega of G. Good. So let me immediately tell you the main result that we'll attempt to prove in this first part. It is basically the fact that it's called a sandwich theorem, and it states that the theta function of G, that is this value, minimum value of an orthonormal representation for G, is sandwiched between two quantities related to the graph. Okay. The first one is it is at least omega of G bar, which is basically the clique number of G complement, and it is at most the chromatic number of G bar. Okay, so this is going to be our main result. Okay, so is this clear? Okay. What we are trying to show today, that this theta function, which is a function defined on a graph G based on certain geometric representation, is actually sandwiched between two very well-known structural properties of the graph, the clique number and the chromatic number, but of its complement. Okay. Okay, there seems to be a line on the screen, maybe by a mistaken annotation. It's fine, it's not too much of a distraction. Okay, good. So one thing is we have already shown one side of this, right? So when did we show one side of this? This part actually we showed yesterday. Because what we actually showed was that the theta function of G is lower bounded by the independence number of G. Okay, and we know alpha of G is nothing but the clique number of the complementing clique number of the complement graph, right? So this should be easy to see. So we have already shown this. And what we'll mainly try to do is related to the coloring or the chromatic number of G complement. Okay, and the way to show this, notice that this has got nothing to do with respect to, about computation or other things, but we'll take a detour um, through certain aspects, through certain computational aspects of the theta function, and that will lead us to this result. When I say computational aspects, I mean how efficiently can one, given a graph G as input, how efficiently can you compute this theta of G? Okay, can you compute it efficiently? Okay, we may not be able to analyze it exactly, but given a graph G, if you feed it into a computer, can it efficiently compute this quantity? Okay, what we had told yesterday in the beginning is that given a graph G, say, even computing the independent set size is believed to be hard. That is, you cannot expect a computer to compute the independent set size. But what we'll see today eventually is that actually computing the theta function of a graph, a computer can do efficiently. Just a second. Okay. Okay, so that's just what we had seen yesterday. By the way, notice that one small thing. Chi of G bar is always at least omega of G bar. And this is kind of a trivial fact in graph theory, right? If you have a clique, you need at least the number of vertices to color it. So if you have a clique sitting in a graph, you need at least the one. What this states is that theta of G is sandwiched between the two. Okay. Okay, so how do we view this computation of theta of G? And the next 15 to 20 minutes, I'm going to spend on this aspect. Okay, so theta of G, the theta function, we had shown like the one way to view it is that it's a relaxation of alpha of G. What do you mean that it's a relaxation? Well, it is basically some sort of an optimization problem. Alpha of G was an optimization problem that asked what is the size of the maximum independent set in G. Theta of G is a relaxation of that. It is still an optimization problem because it says what is the minimum over all orthonormal representations of G of the value of that orthonormal representation. Right. We had mentioned this briefly yesterday, right? That you look at orthonormal representation, it forms a compact set, and you want the minimum over all of this. Okay. The question that we'll be looking at in this first 15-20 minutes is whether a solution to this optimization problem can be computed efficiently. Okay, we may not be able to analyze it again with hand, but then if you feed G to a computer, will it spit out a number which equals theta of G? Okay, so to do this, let us first understand how we view an optimization problem typically when looking at a computational viewpoint. Okay, so you can think of this as some sort of an extremal problem where you want to minimize or maximize a function f of x. X is the variables. Typically for us, they are in Rn or some high dimensional space of real variables subject to constraints. Okay, so I'm not saying what the variables are. So x is not a single variable. So you can think of x as a tuple of variables and say x is in Rn or similar. Okay. Subject to certain constraints, you can have constraints of the form some function of x is 0, some function greater than 0, less than 0. Really, there's no, for a more general form of optimization problem, the constraints can be anything. Okay. And surely you can expect that the more complicated the functions f and g are, right? If your domain, for instance, is not smooth, or if some of you have seen it's not convex or something, you can't expect. You may feel that finding the optimum is going to be much harder, right? So I'm calling the optimum z star. Okay. So finding this optimum may be hard. And on the reverse point, if f and g's are simple in some way, right, then the optimization problem may be efficiently solved. Okay, you can expect this. The simpler that f and g's are, maybe you can expect to solve it. Okay. Now, in most cases of note that we'll use today, I'm going to implicitly assume that the optimum exists. We may see a couple of things that, yeah, so for under certain good conditions, typically for the optimization problems we consider, the optimum will exist. Okay, so let's take one of the simplest ones and many of you might have seen this before. Okay, when the function f, which is called the objective, right, you're maximizing a certain objective subject to certain constraints on the domain. Right? Okay, so here's the most simple thing where f and g are both linear. Okay. So you have only two variables, x1 and x2, in this example that I've given here. And you want to maximize x1 plus x2, which is the objective, subject to, and I've drawn out these constraints here, in a diagram so that it's easier to visualize how the domain looks like. So you have x1, x2 greater than 0. So it lies in this positive orthant. Okay. And then you have linear constraints. For instance, if I say x2 minus x1 is less than equal to 1, here it corresponds to being one side of this half space, right? The area below. Okay. The second constraint says x1 plus 6x2 is less than equal to 15, which is basically this. Okay, and you're looking at the shaded half space below this line. Okay, because you want less than equal to 15. Okay. The third constraint is 4x1 minus x2 less than equal to 10, which is the left of this line that I've drawn. Okay, and the intersection of all of these gives me the possible domain that x1 and x2 can vary in, or these are what I call the feasible solutions. Feasible solutions are pairs x1, x2, in this case in R2, such that they satisfy all the constraints. Okay, and I want to find the optimum of a certain objective function, in this case x1 plus x2. Okay, so how does this optimum look like? Well, x1 plus x2 if you look at this, x1 plus x2 is 0 here, and it's 0 along, let me draw a red line, it's 0 along, say, okay, so it's 0 at this point, right, in the domain. And then it slowly increases as you move in this direction. So this may be x1 plus x2 equal to 2, x1 plus x2 equal to 3, and so on. Okay, this keeps increasing. Now, as I vary the function, so this is the normal vector along which it increases. The value of x1 plus x2 increases. So can you tell me a point looking at this diagram where the optimum value of x1 plus x2 will be achieved subject to being in this green, in this gray region? Okay, can someone tell me where the optimum would be achieved? So there'll be some point where this keeps increasing. And just from the figure, maybe you can guess where the optimum will be achieved.
3 comma 2.
Exactly. So as you move here, just from the figure, no need for a formal proof for now. At 3 comma 2, right, is a feasible point where it looks like x1 plus x2 will be the highest. So the optimum of this optimization problem is equal to 5, and it is achieved at 3 comma 2. Such a program, such a kind of optimization problem is often called a linear program. And a general linear program takes the following form. You have an objective subject to constraints, and typically you can have x greater than equal to 0. And it's not necessary to have x greater than equal to 0, but for our purposes, I'm keeping it in. Okay. And x is in some Rn. Okay, what does C transpose x look like? It's a linear function of x. The objective will look something like summation Ci xi. Okay. What is this Ax less than equal to b? It's just a linear system in the variable x. And therefore, if you have m constraints, A will be in m cross n. This is A. And if you have oops, x less than equal to b. Okay, so this is what this constraint when written out in matrix form looks like, but it's just a collection of m constraints. Okay, in the previous one, we had how many constraints? We had 1, 2, 3, 4, and 5 constraints, right? X1 greater than 0 and x2 greater than equal to 0. I'm clubbing into one constraint. Okay. Okay, in this case, I have put x greater than equal to 0 explicitly, so it takes care of that. Okay. So you have linear constraints. You want to optimize this. And it turns out that an optimal solution to a linear program can be found efficiently computationally. That is, if you have the C, A, and B and feed it into a computer, there's a solver that can find an optimal solution, that is X star, which optimizes the above. Okay. Any questions about this? This is non-trivial to actually show because, first of all, I've not defined what is efficiently, but I'm not going to define that over here. Okay. All you need to know is that it can be found efficiently. So if you feed this in, you will get an optimal solution X star. And of course, you can compute from it what the optimal value is of this program. Okay. Why is it called a program? I mean, it's not, it does not, in case you're not familiar with it, it's called a program because it was used to kind of, when it was first discovered, it was used to make certain schedules. Okay. And those schedules were called programs. It's not a program in the sense of being a computer program. It's an optimization problem. Okay. But the name has stuck, and since then we call it a linear program. Good. So if this is clear, what we'll need is actually a generalization of this in some way. Okay. So now say that the variables are not just x1 to xn, but for some weird reason, I'm going to look at the variables as being arranged in a matrix. Okay. So I have x11, x12. These are all my variables. x1n, xnn, x21. Right. So the variables are going to come from this matrix. Okay, why? I've not told you this clearly yet, but it's useful in applications. So we'll go ahead and use this. Okay. And in fact, I will put a slightly more constraint that they come from a symmetric matrix. Okay, that is x12 is equal to x21 always. So I may just use one variable for both of them when I say xij. Good. So this is the space of variables. You have n squared variables here. Okay, of course, they're subject to constraints. You have symmetric constraints, right? And then let's try to kind of generalize the previous linear program based on this. Okay. I will still write out a linear program here, but I will impose some additional constraint on the variables. Okay. So C transpose X, I'm not going to change at all. It's still going to be a function of the same form. One thing I should say is that although I've introduced it as a maximum, you could also take minimum. It doesn't really make a difference. Maximum, minimum does not make much difference to a computational solver because you could replace the vector C by minus C and run a minimization routine on that. Okay, maximizing C transpose X is the same as minimizing minus C transpose X. Okay. So now instead of summation Ci Xi, I'll have something like this, right, in the objective, a linear objective. Such that now I have ax less than equal to b, right? This seems slightly harder. What do I do? Well, I just replace it by some linear constraints on the variables x. And if I want to write this out explicitly, I will write this out in the following way. So notice that I had n variables here. I have n squared variables over here. Okay, xij. All of these are scalars over here. Okay, so I'm just taking linear combinations of the xij's and constraining them in some way. The same as what we did for linear programs. There's no difference. Until now, this is also a linear program in the variables xij's. For k being, maybe I have m linear constraints as before. I can keep this also in a similar form. But now what's going to change is how I handle this constraint small x greater than equal to 0. What this meant was that each xi is greater than equal to 0. Now I'm going to do something a bit more, like a bit more restrictive in some sense. Or I'm not going to require that all the variables are greater than equal to 0, all the xij's, but I'm going to put a constraint on what the matrix is. Okay. I'm going to say that the matrix X is positive semidefinite. Okay, I think you've seen some definition of what positive semidefiniteness is before. I'll redefine it again. Okay, so this is a constraint on the matrix as a whole. Okay, it is not saying this symbol is for positive semidefiniteness. It is not saying that every entry of X that I'm putting over here is non-negative. Okay, it's not saying that. Okay, it's saying that, if you recall, that every eigenvalue of this matrix is non-negative. That's what it's saying. Okay, and then the constraint is, of course, that X is in sim n. Okay, this piece. So this is almost a linear program in the variables, except for this constraint over here. Okay, that X is PSD. Okay, let me quickly recap what positive semidefiniteness is. Okay, we are just going to use these properties as a black box and maybe not actually refer to it also too much. Let us see this. Okay, so M is a symmetric matrix and it's said to be positive semidefinite. The basic one is you can take it as all the eigenvalues of M are non-negative. Notice that because the matrix is symmetric, all the eigenvalues will be real. and we are saying that they will be non-negative. Okay. The second equivalent definition is that Z transpose MZ, which is the quadratic product, is non-negative for all Z in Rn. Okay, that is if you take this matrix product, sorry, this quadratic product, this is Z transpose. M is an n cross n matrix. Z, this product is a scalar, and this has to be greater than or equal to 0 for all Z. Okay. And the third equivalent definition is that M is equal to U transpose U for some matrix U. This is going to be useful to us. Okay. Notice that 3 implies 2 immediately. It is useful and easy to see as an exercise because if you have Z transpose MZ and I know 3 holds, then this is Z transpose U transpose UZ, which is what? It is just the norm of UZ, 2 norm squared, right, of U times Z, which always is greater than or equal to C. Okay, so this is a easy proof of 3 implies 2. In fact, all of them are equivalent. We'll not go over that for now. We will not show the equivalence. Any question in this definition of what a positive semidefinite matrix is? Okay. Okay, good. So now we are going to start with these. We are going to mainly deal with these kind of matrices when we look at optimization. And a semi-definite program, which is actually a generalization of linear program in some way, although it looks like we are imposing a bit more of constraints, is going to take the following form, and I've written this before. I'm going to have max or minimization. I don't care which one it is because I can flip from one to the other by changing the cost function. The variables are xij's, right? Sorry. Sorry about yeah. Subject to certain linear constraints on xij's. Example, you can have something like 4x11 plus 3x21 plus 5x73 is greater than or equal to 10. Anything of this form, a linear inequality or an equality is considered a constraint. There are linear constraints on the xij's, and the core thing is that x is positive definite and x is in the space of symmetric matrices n cross n. Okay, the variables are the entries of the matrix. Okay? And it turns out, maybe quite magically, that omitting certain technical conditions, we can efficiently find optimal solutions to semi-definite programs. Okay, again, the word program is not, it's not a computer program, it's a formulated optimization problem that because of historical habit has been called programs. Okay. Now, one thing that we have to be careful about is when I told you about linear programs, the sets were intersections of half spaces and they were closed intersections of half spaces. So typically the optimal will always exist. This may not be the case for semi-definite programs. And I will not discuss this maybe in detail now, but if you look at this, the optimum exists in the limit, right? But it cannot be achieved at any point. But it can't be attained in the domain. Okay, which is why when I say I'm going to solve semi-definite programs, I'm going to basically not give you an optimal solution as such, because I cannot produce x's that satisfy it in the domain, but rather will give you an approximately optimal solution. So solvers, which are basically computational programs that if you input gives the answer, solvers will always give for SDPs approximately optimal solution. Okay, that is the solution will be feasible and it will be as close to the optimum. You can get really close to it depending on how much computational power or time you're willing to spend in finding it. Okay, good. So I hope the basic idea of a STP is clear. It's just a linear program subject to certain the positive semi-definiteness constraints. The variables are entries of a matrix that is constrained to be positive semi-definite. Okay. So any questions about this? We don't need to know the details too much of how they are solved. All we need to know is that they can be solved. That's important to us. And this formulation of a STP, that will come in useful to us later also. Good. Now let's go back to the theta function. And I had said that theta of g is an optimization problem, right? So what was the optimization problem of theta of g? Right? You wanted to find vectors for vertices such that they were orthogonal on non-edges, right? And you wanted to optimize the value of such a representation. So what does it mean, right? So it means that I'll just write it out explicitly once more so that it's clear. So G is the graph. Okay, its vertices are 1 to n. You want to find vectors u1 to u1 such that it's an OR ui transpose uj equal to 0 for ij not an edge, which I'm denoting by e bar. And what else? Well, we don't have much else, right? And you want to minimize and a handle C. So all of these are variables. You have vectors and a handle C. So I'll not write the minimum. Okay. I want to minimize the maximum of 1 over C transpose ui squared. Okay. So the minimization, actually, you can think of it as running over all vectors u1 to u1 and the handle C, right? Autonomal representation constraint. Now I claim that this is actually a semi-definite program in hiding. Okay, although the objective looks like it is hidden in this complicated min of max of 1 over C transpose ui squared, right? I claim that it is actually just a semi-definite program. So, can someone tell me, can someone see why? Okay, so maybe not immediately, it's non-trivial, but as I try to explain it, just try to think of it. What I'm going to do is actually write out an equivalent optimization problem to this and then claim that that is an STP. So I'm going to write out an optimization problem, which is basically the following: maximum over t. I'll define the variables. T is a variable. The vectors ui's are variables. For all ij in U bar. And what else do I want from this? T. Okay. Subject to So I claim that the value of this, so what have I written? I've written maximize t such that ui transpose uj equal to 0. The variables are vectors ui and a vector c in Rn and t. These are my set of variables. It may be kind of odd when you look at an optimization problem where the variables themselves are vectors, but it's not very confusing. I mean, you could have an optimization problem with elements coming or the base variables being varying over any domain. This is just one such domain. So I say consider the optimization problem maximum over T such that ui transpose uj equal to 0. Okay, I want to maximize the value of T such that the constraint is satisfied. This is just the orthonormal representation constraint, and C transpose ui is greater than equal to T. Okay, so suppose Z star is defined as the optimum of this. Then the main thing that I want to state is Z star is 1 over square root theta of G. Okay, so this is the main key. Okay, I'll let you stare at it for a bit to understand maybe why this is true. Okay. This again is an optimization problem. One thing that is clear from this formulation is that my ui's and uj's are vectors, right? So they can vary in any space and so see. So immediately what it looks like is that the ui's, just given this constraint over here, okay, they have to be an orthonormal representation. Okay, because I've enforced it explicitly in the constraints. Like there's nothing more to that. I've enforced it explicitly in the constraint that ui transpose uj equal to 0. Now, why is the objective value equal to 1 over square root theta of g? Okay, and I've also said that they're unit vectors. C looks like the handle, right? So it looks like, but why is t equal to 1 over the square root of the value of the orthonormal representation? Okay. Notice that the theta function objective here is maximum over I of 1 over C transpose ui squared. Okay. That means that if every C transpose ui is greater than equal to T, right? Every C transpose ui is greater than equal to T, then what is this value? Okay, this looks like 1 over T squared, right? And that is basically the idea that theta of G is going to be nothing over 1 over Z star squared. Okay, so another way of writing this is okay, so whatever the T value comes for a certain orthonormal representation that maximizes this, right? You can keep increasing T, okay, but there'll be a point that maximizes, and that T, since you're maximizing it, but T is upper bounded by C transpose ui. Right? So it'll be equal to the maximum over I of 1 over C transpose ui, or the minimum of C transpose ui squared, C transpose. So why is this equivalent to this? The reason is that uh, for any set of vectors ui that are satisfying the other constraint, the value of T that will be set. Let me write it here for lack of space. For any feasible u1 to un and C, that is any set that satisfies the other constraints on them, the best T or the optimum T is going to be, so T has to be always bounded by all of them, and this is for all I and n. T should be set because I'm trying to maximize T. The maximum that I can push it to is the minimum of C transpose UI. Right? And because it is the minimum, so 1 over T squared gives you exactly what you want. It gives you this way. So this we are going to use. That you can formulate it in this equivalent optimization problem. Okay. Now, one thing that I'm going to say next is that this optimization problem is just a semi-definite program in hiding. Okay, so this is basically a SDP that is sitting over here. Doesn't look anything like a SDP because you seem to have the variables as vectors, whereas if you remember in the SDP formulation, the variables were entries of a matrix which were positive semi-definite. Here I have vectors, and every vector is this high dimensional object. So what are the entries of this matrix and why is it the same? Right? So let's do that. So I claim that the above optimization problem is actually a SDP. Okay, or the previous one, there's nothing. Okay, so let's see how we wrote it. We wrote it like the following: max over T such that UI transpose Uj is equal to 0. Excuse me. For all ij in E bar, and C transpose Ui is greater than equal to T, right?